Hi, I'm Adolph Oliver, and this is a video clip about inverse functions. Now, what do we mean by an inverse function? Well, what an inverse function does is when you do the original function and end up with some value, the inverse will take you back to the original value that you had. In other words, what an inverse function does is it undoes the math operation of the original function. We use this a lot in math. I'll point that out to you in a little bit. But let's look first at a fairly straightforward example. I think it's easy for you to see that if you square some variable, x squared here, that if you want to get back to the x, you take the square root of that. Well, x squared and the square root of x are inverses of each other. Now, we could define the original function, f of x, as equal to the x squared. Then I could say that f negative 1 of x. Now let's explain what's going on here. We use the same letter, so we know that we're taking the inverse of this guy right here that we started with. How do we indicate it's the inverse? Well, here's what they do in math on this. They put a negative 1 up here. This looks like an exponent, but it's not. It just indicates that this is the inverse of the f function. So if you have functions defined here and you see something like this, you just have to realize that means it's the inverse guy. It's not a negative exponent. Well, okay, if the original function is x squared, the inverse has to undo the square, and that's the square root of x. Now, let's remind you, if x were to equal 2, then in the original function, we'd take 2 and square it, and we'd get 4. Now, look what the inverse does. You take that 4 and plug it into the inverse. That's the square root of 4. That gives you the 2 that you started back with. So this is what we mean by inverses taking you back home here. Now, we could also do this. You can define the original function as the square root of x. I mean, if these guys are inverses of each other, you can start out with either one. So if we say f of x equals the square root of x, now we say f negative 1, the inverse of this guy, okay, equals x squared. And again, you can see this. Let's say that x is 9, the square root of 9 is 3. Well, how do you get that 9 back? You plug it into the inverse over here. 3 squared equals 9, so you're back to your original 9. Okay, well, this gives you an idea of how these inverse functions work. Now, let's go down here and talk about them a little bit more here. Inverse functions are used all the time in algebra. They're how we solve equations. For instance, if you get y plus 3, remember we want to get rid of this plus 3, well, we hit it with its inverse. The inverse of plus 3 is minus 3, but we have to do it to both sides, so we get y equals x minus 3. You've been doing this for quite a while. In fact, probably all the way back to 3rd or 4th grade where you first learned to add and subtract. But anyway, we're finally telling you these are inverse operations. If you're multiplying or dividing, here's 5y equals x. And you know you divide both sides by 5. What's the inverse of multiply? It's divide. And we get y equals x over 5. So this inverse operation business is actually something that shows up a lot in math. Now we're officially telling you about it. Now, in a recent section here, we talked about what a function was. And a function requires that if you give it an x value, and that of course is in the domain of the function, that x value then always has to go to the same y value which is in the range. So that was the requirement for a function. If you keep giving it, x equals, let's say, 5, and then y comes up 9, every time you give it x equals 5, you better get that 9, and that's what makes it a function. But there is no requirement that the y value, the 9, goes only back to the 5. It could go to some other values. Well, that's fine for just working with functions. But if we want to work with inverses, we need to make sure that that y value goes back to the same x. So let's introduce you now to a little bit tighter type of function here. So here we go. To have an inverse, a function must be a one-to-one function right here. Now, what do we mean by one-to-one function? Well, here's a couple of cloud representations and some x domain values and some y range values. And I haven't shown all the things that match up. We're just concentrating on one here. So if we give x equals 3 in the function and it gives 8, by, of course, the normal function definition, every time you give it 3, it better give you 8. Now, what makes this one-to-one is that we have to go back to where we started from. So, anytime you have 8 in the range, it has to go back to 3. It can't go to anybody else. If it does, it's not one-to-one. Well, if you have a one-to-one function, then you're able to come up with the inverse of it. Now, many functions are indeed one-to-one, and in some of the homework examples we'll be doing for you shortly here, we'll be going through these steps to show you how to come up with the function and its inverse. Okay? So here's the steps that are going. I'm just going to mention them to you now so you have an idea of what we'll be doing. The original f of x, we're going to replace that with our old letter y. And the main reason we do this is it just makes it easier to write down. But here's the real thing that's going on here. Interchange the x and y variables. In other words, where you see x, write y. Where you see y, write x. Now, what this does is it maintains the operations we use, like in T charts and tables and stuff like that. The independent variable is the one that we pick, and the dependent variable is the one that we calculate. And since we're turning around and going back the other way, we want to interchange the x and y, so we still have that independent-dependent operation going on. Okay, once you do that, you solve for y equals. And if you can solve for y equals, then it has a inverse. And, of course, at the tail end then, replace the y again with f negative 1 of x. That's just to indicate now that this is the inverse of the original f function. But now, here's one other thing we want to talk about. Inverses can always be tested. Now, if you get an inverse like this, it should follow these rules if you didn't make any mistakes. But if you had just two other functions and you want to see if they were inverses of each other, this could be used. Okay, here's where we start making use of some composition. So let's take a look at what's going on here. Okay, there are two requirements. F composed of f negative 1, okay, of x. Now remember, in composition, the second guy always gets substituted into the first. Okay, well, if you do that composition, leave the x in the original equations, it all has to reduce down to just a single x. But you also have to test it the other way around. F negative 1 composed of f. So now you're plugging f into the inverse. It also has to give you x. So both of these must be true for your f and f negative 1 to actually be inverses of each other. Now let's show you this in a simple example again. Here just a little while ago we showed you that f of x equals x squared and f negative 1 of x equals square root of x, that these guys are both inverses. We just plug some numbers in and you can see that plain enough. Okay, but using this test, here's what we have to do. Okay, so let's assume that we're going to keep the f of x to be x squared and the f negative 1 of x to be square root of x. And so you have to have f composed of f negative 1. That means the f negative 1 is going to be plugged into the x. Well, okay. What's the f of x? The f of x is x squared. So I make a set of parens and square it. Who am I plugging into that? What I think is the inverse. So here's the square root of x inside. Well, what happens when you square the square root of x? You get just a plain x again. But now, this also has to be true the other way. You have to compose f negative 1 and the function. So the function, if you plug it back in, also has to give you an x. Remember, here we're just indicating we're not putting numbers in, we're just leaving the variables. Well, okay. The f function is going to be plugged into the f negative 1 guy. The f negative 1 guy we have here is the square root. So here's the square root. But now what we're going to do is replace the original x here with what f of x is. So here it is. I put the x squared inside. Well, you can see the square root of x squared equals x. So since both of these guys resolve to x's, they are indeed inverses of each other. Okay, here's an example where we're going to test to see if these two guys are inverses of each other. We didn't come up with these ourselves, somebody else did, and we want to see whether it's true or not. So notice at the time being here, I'm not claiming that if this is the f function here, that this is f negative 1. We don't know that for sure yet, so use any letter here like this. But the idea is now these guys are only inverses if we can compose them both ways and they give us back the letter that they started with. In this case, it's going to be n. So here we go. The first test I'm going to take f of n and compose, there's my circle, with h of n. Okay, and we're going to keep the n's in there, so I indicate it like this. Okay, well remember, it's always the second guy being plugged into the first guy. So the first guy here is negative 2 minus 1/5 times n. Well, I make a set of parens for the n because what we're plugging in is the second guy here. That's how composition works. You always take the second guy, plug him into the first. So he's negative 5n, okay, minus 10. Okay, well, let's continue on with this and see what we've got. Okay, the negative 2 out in front comes along for the ride for the moment. But now we have to distribute in, okay, the negative 1/5 in front of the parens. So minus times minus gives me plus. The 5's cancel each other out. So I end up with just n over 1, or n. The second guy, minus times minus gives me a plus again. And 1/5 times 10, well, if you reduce it out, you end up with 2, but 1/5 of 10, I think you probably see is 2. Well, look what happens here. The minus 2 and plus 2 knock each other out, and there it is. We're just left with n. So it passes the test going this first way, but it has to go both ways for it to be the inverse. There are cases where you get it to work one way in a composition and not in the other, which means that they're not inverses. Okay, the second guy, we go the other way around. We take the h of n and we compose it with the f of n, and of course we keep the variable n in the equations here. Okay, once again, second guy goes into first guy. Composition is real easy, that's all you have to remember. So let's go ahead and follow what we're going to do now. Okay, so the original h of n, let's go back up and look at it up here. the original h of n was negative 5n minus 10. Okay, so this is going to be negative 5. I make a hole for the n minus 10. Okay, so remember, negative 5n minus 10, I'm going to replace the n with the second guy. Well, the second guy is my f function. So I have in here negative 2 minus 1/5 n. Okay, negative 2 minus 1/5 n. That's this second guy here plugged into the first one. Okay, well, that's our composition. Now we got to clean it up and see what happens here. So here we go. Take the negative 5 and distribute it in. Negative 5 times negative 2 is positive 10. Negative 5 times negative 1/5, well, minus and minus give me a plus. Let's see, 1/5 of 5 is just 1. I'll put a 1 here to rub that in. And then we have the n. And then there's the minus 10 on the end here. Well, okay, you can see this is going to work because plus 10 and minus 10 knock each other out. And plus 1n, well, that's just n. So, since both of these guys gave you back the variables that were in the original function here, the n's, okay, then these are inverses. Okay, here we're going to find the inverse of this equation. And remember, there was 4 steps we talked about. I'll mention them all again for you here. So this is what our g of n function is, and n is a variable that's in it. Well, the first step that we do here is just one that makes it easier for us to do the rest of our calculations. Take the function notation, in this case it's g of n, and replace it with y. Okay, now here we go. We've got negative 5/7 n minus 15/7. Okay, now the next thing we do, this is to maintain the independent-dependent relationships, like that we use in table of values, for instance. And we interchange the variables. So where I see y, I'm going to write in. The numbers stay where they are, but where I see n, I write y. Okay, here we go. Now, the third step on this is to go ahead and solve for y equals. So here's what I'm going to do. I'm going to jump the term with y in it over to the right, and then this term with n will move over to the other side here. So here we are. I've got negative 5/7. Okay. Actually, when it goes over here, it goes over as positive 5/7. Remember, the sign changes when you jump it across the equal sign. So plus 5/7 y equals, now this is a plus n here, so it'll go over as negative n and minus 15/7. Okay, well now, we got to solve for y equals here. So what we're going to do is multiply both sides by the reciprocal of this. So here we go. 7/5, okay, is the reciprocal of 5/7. And we have to take this whole guy and do the same thing to maintain our balance in the equation. Okay, these guys cross cancel, of course, so I get y equals. Now, distribute this in, okay, so I've got negative 7/5 times n, here it is, negative 7/5 times n, and then let's see, we're going to have negative. There's only one minus sign here. But we can do some cross-canceling here. 5 goes once here, it goes 3 times here. And the 7s cancel each other out. So this is 3 over 1, so it looks to me like it's just negative 3. Well, okay, we were able to solve cleanly for y equals. So that means then that this is the inverse. There's one last step, and that's just to kind of pretty it up here. We turn around now and replace our y with f, well, not f, g of negative 1, because that's the function letter used. So g negative 1 of n, and that's, I'm just writing that in. There's no change here other than just making it fancier, equals negative 7/5 n minus 3. So there's our inverse right there. We could test it if you took and composed both ways the original g function up here, okay, with this. They'd both compositions would equal n to prove that you're correct. Okay, here's another example where again we want to find the inverse of the function that we have, and they're using letter g again. Using the letter you want, doesn't matter. So we go through our 4 steps again. Okay, remember the first step, we simply replace the g of x with y, and that's just to make it easier for us to write as we go along here. So here we are, y equals in the x cubed minus 1. Okay, now the second step, interchange the variables. So y becomes x, and the x becomes y, and it's cubed like the x was here, minus 1. Okay, now the next step then is to turn around and solve this guy for y equals. If we can do that and come out with nice clean answers, then it does have an inverse. Okay, so first thing I'm going to do here, I don't want to make this negative, so I'm going to jump the whole sides. Y cubed minus 1. Remember, when you interchange the sides, none of the signs change. You just do this. Now, the next thing I can do is I want to get rid of this minus 1, so we know in solving equations we add 1 to both sides. So now what I've got here is I've got y cubed equals x plus 1. Okay, well now to get y, I've got to take the cube root of both sides. So here we are. I can indicate it like this. The cube root of y cubed is just y. Okay, and since it's cubed, it's an odd power. We don't have to worry about the answers being plus or minus here. The signs are either positive or negative depending on what the y is, so we're good. And well, we're looking at the answer over here. Okay, the third root of x plus 1. Now, the only thing we do in the fourth step is pretty this up a little bit, and we acknowledge then that the original function had the letter g here, right? So since this is the inverse of that function, I'm going to write this as g negative 1 of x equals, and of course the right side is exactly like we have here, the third root of x plus 1. Okay, there's our inverse, and again, if you were to compose both ways, the original guy and this guy, you'd get both of them to equal the variable x, which would prove that they are inverses of each other. Okay, here's one last example for us to look at, and again, what we want to do is come up with the inverse to this guy. Now, one of the things, note here, that we cannot have x equal to 1 on this because the thing would be undefined. But let's go on here. First thing we're going to do again, the 4 steps. Okay. First off, just to make it easier, we're going to take the g of x and turn it into y, so we don't have to write as much. And then we have over here 3 over x minus 1 minus 1. Okay. Well, the next thing we have to do is interchange the variables. This again preserves the independent-dependent relationships. And so the y becomes x. This equals 3 over x. This x has to become y. Let me scratch that out. I got a little bit ahead of myself, but there we are. Y minus 1, and of course we got this minus 1 in the end. So let's be sure, you got to make sure you do this right here. The second step, where you see y, you replace it with x. Where you see x, you replace it with y. Okay, now, here we go. What we want to do is now solve for y equals on this. Well, here's one of the things that we can do. This negative 1, I can jump over to this side and make this x plus 1 equals 3 over y minus 1. Now, what am I up to? Well, if I make a single fraction out of this, then here's what I know. I can turn around now and cross multiply these guys and come up with a solution for this. So let's see what we got here. Okay, we're going to have x plus 1 times y minus 1 equals 3. Okay, well, this one's going to be a little bit messy to work with. Here we go. We got 2 binomials to multiply here. So I've got xy, okay, and that's doing the 2 first. Doing the 2 last, I get minus 1. Doing the 2 rainbows, I'm going to have minus 1x, so I can just write that minus x. And then I'm going to have plus 1y. There we go. And that equals 3. Okay, well, here's what we want to do. We want to solve this again for y equals. So notice, there's a y that we can factor out here. And so what I'm going to do is take these 2 guys right here, factor a y out, and I'm going to end up with x plus 1, okay, and I've got a minus x. Now, let's make sure here now as we're going through this, okay, here we are. I can scoot it up here so you can see all this. Here it is, I'm multiplying the 2 binomials. And here it is, just using regular old FOIL to multiply it out. I took these 2 guys, put them together here, and factored out the y. So I got x plus 1. And then we got negative x minus 1 equals 3. Okay, let's jump these 2 guys over to this side. So I've got y equal to x plus 1. Okay, equals... Well, the negative x will go over as positive x. Negative 1 will go over as positive 1, so this is plus 4. Okay, the last thing to do here then, let's keep scooting this up so you can follow it along. Gonna divide, remember we're solving for y, so divide by x plus 1 on both sides. Here we go. Okay, these cancel out, so I get y equals x plus 4 over x plus 1. Okay, Well, the only thing left to do, step number 4, is just to acknowledge that the original function up here used the letter G. So we're going to go back and replace the y now with g of negative 1x. This tells us that this is the inverse of the original g function. And what it equals is x plus 4 over x plus 1. Okay, a little more work involved in this guy, but again, the 4 steps that we go through here, changing the function notation to y, interchanging the x and y variables, turning around and solving for y equals, which took a little more effort here, and then at the tail end, the function g negative 1 of x, that just acknowledges that this is the inverse of the original g function. Here it is.